Hi, Mackenzie. This is question 20C. You had mentioned in your email that you had some errors in this. So I'm just going to quickly go through it with you. So I'm just copying the question down so you can see. If you do a direct substitution of -3 for x, you would have -3 quantity squared plus 5 times -3 plus 6. And that'll be 9 minus 15 plus 6, which happens to be 0 over 0. So this actually is good. If you have 0 over 0, that means that there's a common factor between the top and the bottom, and that'll simplify and reduce so that we can calculate the limit. So notice here I'm writing the limit notation. I'm going to factor as x plus 2 and x plus 3. And then I think I noticed in your work that you didn't write the limit notation. I could be wrong. I may be remembering somebody else's. Anyway, so now you need to substitute in now that you cancel the bad factors out. So you have -3 plus 2, and the result is -1. All right, so 20D is similar, but you have a radical expression on the top, and you have the square root of x minus 4 over x minus 16. So if you do a direct substitution again, you get square root of 16 minus 4 over 16 minus 16, another 0 over 0. So once again over here, the technique we're going to use is rationalization, but as long as I have the variable x, I'm writing my limit notation. So I'm going to multiply top and bottom by the conjugate of the numerator, which is root x plus 4. So it goes to the top and bottom. Now don't distribute the denominator, because this is the bad factor that you want to leave exposed so that it'll cancel with hopefully the same factor on the top. And you can see that's why we used conjugates, because if I multiply these two together, I get x, and you don't have to FOIL it out because the outer and the inner will cancel. You just get x minus 16. And that's why we left the x minus 16 separated on the bottom. So that bad factors go away. So you have, now I'm going to substitute in for x. So it's 1 over the square root of 16 plus 4, which is 1 over 8. Okay, now on to the limits involving infinity. So you have 20e, it's a limit as x goes to infinity of x squared plus 3x minus 15 all over -2x squared. So in the video you might have seen that if the degree of the top and bottom are equal, then there's a certain pattern. And this arises because when x gets really, really large, these are the dominating terms. All these other smaller degree terms, I call them small change. Okay, and I think the example I used in my video was if you're a billionaire, all this is small amounts. You just focus on the leading terms. So in other words, this limit is equivalent to another limit. Notice the limit notation is still there, but you only write the leading terms on the top and bottom. And this reduces to just -1/2. And now I drop the limit notation. So anytime the degree of the top and bottom are equal, you'll notice a pattern, okay, that you get the limit to be the leading coefficients, constant coefficients that come out of the leading terms. If you were to type this into your calculator, go to y equals, and make sure you put parentheses, so you have x squared plus 3x minus 15 divided by, again, parentheses, -2x squared minus x plus 1. Now I'm going to go to the table and change it to ask mode if you haven't already done so. I'm going to delete all this. Now x is approaching infinity, so let's try 100. Let's try 1,000 or 10,000. As you can see, the y value is approaching -0.5, which is the same as -1/2. Okay, so there's a double check for you using technology. All right, in 20F, there's a subtle difference. X is approaching -infinity, but the thought process is the same as if it were positive infinity. And now you have the degree of the top is greater than the bottom. So once again, we're going to ignore small change, small change, small change. Focus on the leading terms of the top and bottom. Now, unlike the previous case where the x squares canceled out, here you have an x remaining. So you're going to write the limit notation still So you have 5x over 3. Now think of this as a really, really large number times 5, which is even larger. Dividing by 3 isn't going to really make a difference. This is a negative infinity. So this is really 5 times a really, really large negative number divided by 3. Okay, so it's going to approach negative infinity, or we say the limit does not exist. Once again, let's try this on the calculator. So you have 5x squared minus x plus 2, again, close the parentheses, divided by parentheses again, 3x plus 1, delete all the other stuff, go to the table, and negative infinity. So let's try negative 100, negative 1000, and so on. Notice how the values in the y column get larger and larger and larger. So you can see it's negative 1.7 times 10 to the 9. It's approaching negative infinity. All right, one last one, limit involving infinity. This time the degree of the top is less than the bottom. Again, keep the one term on top and the leading coefficient. This is your small change. We can drop it. Still writing the limit notation, okay, since we have x present. This time it's the x is left in the denominator. So it's like saying you're taking $6 and dividing it amongst uncountably many people. Really, really, really large number, and something even bigger than that. So people get virtually nothing. That means that the limit is 0, because that expression is approaching a very, very small number. And again, you can check this as well. I'm going to type in 6 divided by, in parentheses, 3x minus 5, and go to the table. I'm going to delete all that. X is approaching infinity. Build up, and you'll see that the y value gets really, really small. That's 0.00002. Okay, so the limit approaches 0 because you have an e minus 7 here. All right, I hope that answers your question. If not, do write back and let me know.